So, let us begin with a simple demonstration of how ARMA models are fit in R. I will show you later on how to simulate, but let us say I am given a series Vk. I do not want to show the simulation part right now, because I just want to make it as realistic as possible, so that the real model is hidden from you. I have now the R Studio with me, and a fairly simple set of commands. You are probably aware of most of them by now. So, what we will do is we will look at this series Vk. As I always say, when you are given a time series, do not, and you are asked to build a model, just do not straight jump to ACF, PACF and ARMA model and so on. The first thing that you want to do is you want to really break the ice with the data, and you want to therefore plot the series. So, let us do that as a first thing, and here you have the plot. I am going to zoom it out so that you can see it better. The reason for visually examining the series is to see if there is anything that you can just spot by the eye. For example, some trends or oscillatory features or outliers and so on. And that is actually really useful, because certain decisions that one has to make and also certain validations that one has to make in the course of time series modeling really hinge on your ability to visually observe to do that, and your ability to visually observe something comes about only if you plot the series. So, it is a very good habit, even if you have simulated the series. In this case, I have simulated the series, and even then I am looking at the data, because a lot of times we may have some model in our minds and we may end up instructing something else in R, so that the series is completely different. So, you want to really make this a habit in not only in this course, but in all exercises of data analysis, that you plot the series. So, when you look at this series here, nothing really straight away tells us that there is a trend or that there is an oscillatory feature and so on, and there is only a beginning, right. If you have any kind of inkling that there is non-stationarity in this, for example, an integrating effect and so on, then there are unit root tests available, which we shall talk about later on. At this moment, we will say, okay, as a preliminary thing, I do not see anything non-stationary here, no trend and so on. I will assume stationarity and proceed. Generally, if you make a wrong assumption and if you are careful and doing a systematic analysis, at some point you will figure out that you made a mistake. So, not to worry so much. All right. So, let us actually get back, and now generally the next step is to do some kind of a simple non-parametric analysis, look at the mean, variance and so on. So, we will ask, for example, for the mean of it, very simple statistics, not that I am going to say the 0.23 is very familiar and so on, nothing like that. It is just to get a feel of the data. Of course, when you look at this is a sample mean that we have computed, it is not a theoretical one. Now, at this stage one can set up a hypothesis test asking for the test where you test for zero mean. You can set up a zero mean hypothesis test. In other words, you can conduct a hypothesis test with the null hypothesis as mu v is 0 against the alternative that it is not. And of course, we have not gone through the formal hypothesis test, but the videos that video lectures that you have been hopefully listening to do tell you how to conduct hypothesis test. We will go through that when we discuss estimation theory. So, 0.23 may seem quite high on the face of it, and that is where the hypothesis test is going to come to your rescue and help you conduct a systematic test rather than just looking at the face, taking things on their face value. If we are a layman, as a layman we will say 0.23 is fairly high. So, maybe the mean of the series is not 0, but at this moment we will not go through hypothesis test. We will, through the help of modeling, even be able to answer this question. Okay? And in general, I also want to tell you, until now we have been looking at models for processes with zero mean. For example, if I have written an AR1 model, then I have written this kind of a difference equation, and this is fine as long as the process is of 0 mean. Suppose the process is non-zero mean, then the, and of course stationary, we are still living in the stationary world, then the model changes to this. So, in other words, instead of building models for Vk, you would be building models for Vk minus mu, departures from the mean, and that is a standard thing even in deterministic world. For example, in the deterministic world, if I have let us say some relation between y and x as y equals mx plus c, is this a linear model? Initially I heard lot of yes whispers. It if you go by the traditional JE coaching type thing, look at the power of x and so on, then it appears linear, but from in a strict sense it is not, because it does not satisfy the basic requirements of a linear relationship, a linear mapping, which is the principle of superposition or even homogeneity. So, x if it gives you y, alpha x does not give you alpha y. So, in this case we do not call this as a linear, we call this as an affine relationship, which can be transformed into a linear relationship by constructing what is known as a model in terms of deviation variables. So, if I have a reference point x naught y naught in the 2 dimensional space of x and y, then I could rewrite this model as y minus y naught equals m times x minus x naught. Okay. So, in such a case, as you can see, what we are building is linear model, but in terms of deviations of y from y naught. So, you can also think of this model in this way. Ek still remains as a 0 mean, right. The other way of looking at this model is to rewrite this model in terms of this, but add an intercept term. So, you could say that there is some alpha plus Ek. So, you are now transferring the non-zero mean nature of V to as if you have now an Ek. So, you can think of this alpha plus Ek as a new Ek with non-zero mean equaling alpha, but this alpha has a relationship with d1 and mu, and what would be the relationship? So, what would be alpha here for us? d1 times or mu times 1 plus d1. Okay. So, it does not matter, essentially what this tells us is if you have a process with non-zero mean, either you think of this model, that means you subtract the mean and then fit a model, or you fit a model with an intercept term, your usual model with an intercept term. And this is important because when I pull up the help on this routine which estimates the ARMA model for you, it will ask a few questions from you. Do you believe the mean is 0 or not, and so on. So, you have to supply some inputs. At that, so using those options, we will be able to answer the question for this series whether this null hypothesis holds or not. All right. So, now we can also look at variance of Vk, not that it is going to tell us a lot, just for information's sake. In fact, we can ask for some summary statistics, right, which gives you the minimum value, the maximum value, the mean, median, and so on. And one of the things that I have also said, let me see if you can give me the correct answer with regards to this question of what we should check for before even proceeding to building an ARMA model, or it is a linear model that we are fitting. Is there anything more that I should do before jumping to computing sample ACF and sample PACF? Sorry? I am sorry? Any answers? Is there anything else that I need to look at? Any assumptions that we make on building linear models? Stationarity is anyway something that we have said visually, yeah, I do not see any evidence at the moment.
We want Gaussianity of the.
Correct. So, that is something that we assume Gaussianity is not necessary for building a linear model, but necessary for the optimality, in the sense if the model that you are going to fit is expected to give you an optimal prediction, optimal in the sense as good as your conditional expectation, then you are assuming joint Gaussianity. So, you want to be able to see if the series has some kind of a Gaussian distribution or not. Obviously, we are working with a single realization, you can't really do much, but there is something that you can do without instead of just skipping that step altogether. So, we can look at a histogram, at the histogram of the series and ask if the distribution looks Gaussian, right. It is a sample distribution that we are constructing, it is from a single realization, and I think all of you are able to see the plot, right, or I can actually zoom it out for you so that you can. So, here is the sample histogram that we generated from the given realization, and there is a strong indication that it is it has these observations have a Gaussian distribution. Of course, again here one can go through a formal test of Gaussianity. There are Gaussianity tests, we will not go through that, but you want to make note of these tests these steps, and again write against each step that some steps we are just doing in an informal way, and later on we will do the most important steps very rigorously. All right. So, since we are more or less convinced that it is stationary by visual inspection, Gaussianity at least through histogram calculations, it is fine. Even otherwise you are okay to fit an ARMA model, please keep that in mind. Just because you find a non-Gaussian distribution, you should not completely apply the brakes and close your laptop and enjoy, open your phones. So, do not do that. You can still fit an ARMA model, get decent forecasts and so on. All right. So, let us now get into the time series aspect of it. So, now we want to see if there is any scope for predictability where we turn to ACF, right. And here I am using the ACF routine in the stats package, and of course, here we can ask for a maximum lag of something like 20, 50 and so on, 30, 50 and so on. We will just use the defaults. By default it plots the ACF, and there is an option that you see, I do not know how well you can see, here it says among the many options there is something called d mean equals true. Okay. Unfortunately, I do not know how well it is visible to the people sitting in the back, but there is an option, and that option has got to do with whether you want to use the standard definition of autocovariance function where we subtract the mean, or the signal processing or the engineer's definition of the ACF where we do not subtract the mean. And sometimes it can make a difference, but here we will stick to the standard one. As I said, throughout the course we will use the standard one, and the default is it will plot correlations for us. So, here is the ACF. So, I hope all of you are able to see this plot, and this is where if we have made a mistake on stationarity assumption, for example, remember non-stationarities are of different kinds, not all non-stationarities can be picked by the ACF. There are different types of non-stationarities, non-stationarities in the mean, non-stationarities in variance. Within non-stationarities in mean you have trend type, which are deterministic type non-stationarities, and you have the stochastic ones which lead us to the random walk type non-stationarities and so on. But among the variance non-stationarities, the variance can change with time for the process, and your ACF may not be able to pick that up. It may still show you a decaying kind of ACF. So, relying on ACF for checking for non-stationarities is a good thing to do, but one should keep in mind that it does not detect all types of non-stationarities. So, if there was a trend type or if there was an integrating effect, one could easily expect a slow decay of the ACF, but that does not seem to be the case here. And at this stage, if I look at the ACF, what are the inferences that I can draw? Any obvious inferences that just speaking to you, the ACF is telling you, look, this is what the series can contain or can be thought of. Why is it so difficult? So, the question that comes to mind is because we are doing this for modeling. First of all, does the series have predictability? It clearly has, right? The estimates are way at least there is one estimate which is significant at non-zero lags. That is the first point. Second point is now we want to ask which model is suited, whether it is MA or AR, and that is where we start looking for certain signatures. And what kind of a signature do we see here? AR model, exponential decay. Anybody wants to debate that? No, it could be a moving average model of high order. No? Possible, right? Because after all these are estimates and they do not carry the exact theoretical signature. So, that is the ambiguity with which we are always presented when it comes to time series modeling, and then one has to carefully explore different options and come up with a suitable model. So, at this stage, if I were to think of a moving average model for this process, then what would be an appropriate order to start with? 9. Okay, so we have Navagraha, so we have here 9th order, excellent. But if I were to now think of this as an AR, because maybe I can think of the decay as exponential, then I can turn to PACF because 9th order seems a bit high. Generally speaking, you should be able to model a lot of stationary time series processes with fairly low order ARMA or AR and MA and so on, unless you have some special series that are waiting for you during maybe exams and so on. But so, let us turn to PACF and ask what story it has to tell us. So, this is a PACF for you, and the PACF tells us some other story with, and it says, yeah, you can think of this as an AR model of 5th order, right. So, in terms of parsimony, AR seems to be the winner with respect to MA model, but we have another choice too, which is ARMA. And as I have said, none of these ACF and PACF truly tell me what could be a suitable order if I were to fit an ARMA model. ARMA model orders are generally found by trial and error in a systematic way. So, at this stage, instead of fitting an MA9 and checking out, we can actually start off with AR5 because there is no other information available to me. And when there is no other information available, generally the preference is for AR models because of ease of estimation and so on, and in this case mainly the principle of parsimony is telling us that a 5th order AR is perhaps better suited. In some other case, it may be that the AR model is 10th order, a 10th order AR model actually is suited to the series vis-a-vis an MA2, then you may want to pick up the MA2. Okay, so that is option number 1, we can fit an AR5, but given that it is AR5 and MA9 and so on, there is a chance that the underlying series is actually coming out of an ARMA process, correct. And because we do not have any indication of what is a suitable order, we start off with ARMA 11. So, there are 2 models that we are going to fit, one is an AR5, another is an ARMA 11, all right. So, let us do that. Now, when it comes to fitting AR models, as I told you already, because AR models give rise to linear predictors and therefore, it is much easier to estimate the parameters. There are special routines, and we have talked about Euler-Walker's method, we have spoken of Levinson-Durbin's algorithm and so on, and then there is a Berg's method and so on. So, there is a separate routine for estimating AR models, and the routine is simply AR. You can pull up the help on AR. I am sure you are, at least in this room, you are unable to read the help unless you have a magnifying lens right in front of you, but and unfortunately, I do not know how to increase the font size in the help window. But if you look at the AR command, of course, apart from asking for the series, it is asking for an important piece of information from the user, what is the order that you want to fit. And let me read this for you here. It says that apart from supplying the series, the second option is AIC. AIC stands for Akai case information criterion. Okay. It is an information criterion, information theoretic measure derived by Akai K using information theory concepts. And it is a Boolean variable. Setting AIC equals true allows the routine to pick among a range of orders, pick a model with a suitable order among a range of orders that the user specifies. We said fifth order is good, but it is only a good guess, we do not know if that is a final answer. So, maybe as a user I would think 5 to 7 is what I want to explore, and I can specify that through the third argument, which is listed as order dot max. And again, if you set AIC true, then it explores all orders from 1 to this maximum specified order. If AIC is set to false, it will freeze the order to the maximum order that you have specified. Okay? And then there are other options here. For example, it is asking for the method that you want to use, whether you want to use Euler-Walker method or you want to use Berg's method or ordinary least squares and so on. Right now, let us not worry about the methods. When we move to estimation theory, we will know what are all these methods. We will just stick to the default one, maybe the default one I think is Euler-Walker. And then NA dot action. So, many a times your series can have missing data, and NA stands for not available. So, it is asking, if you give me a series with missing data, what do I do with it? Do I actually get scared and stop working, or do I just ignore it, or do I just linearly interpolate, omit it? That one has to specify. Right now, that is not something that we should be worried about. And then there are other options that you want to see that you can give, and if you want to actually get a full list, it is given here. There is an option for d mean, and that is important. That means, should I estimate the mean or not? If I set d mean equals true, d mean means removing the mean. So, whether you want to fit this model or this model. So, if I set d mean equals true, it is going to fit this kind of a model and get you an estimate of I believe the alpha. In fact, it is unfortunately, and this is one of the things that is also discussed on Stauffer's website on some of the fallacies that you have with this routine and the terminology that is used in R. So, although it says it is going to fit a model like this, ultimately it is going to report alpha, but that does not matter. In the sense, what you want to know is whether first of all alpha should be in the model or not, because if alpha is 0, mu is 0, because of the relation that we have between alpha and mu. That is the first thing of concern to me. If it is not, then from alpha we can always figure out what is mu, because the model, the routine estimates d1 for me, right. So, we can set d mean equals true and then let the algorithm tell me what it does. Now, we can do that. So, let us actually do, then there are other options, do not worry about the remaining options and so on. And in every, when you look up the help on any routine, also understand apart from what it needs, once it is done what it returns, and that is usually described under the value. So, it is telling you what are all the things that it is actually going to come back with, and it is going to come back to you with, of course, the AR coefficients, the order that it has selected Of course, if you set AIC equals false, the order is going to be the same as you have supplied as order dot max, and then it is actually going to give you the variance of the prediction error. It is going to report, it says x dot mean, it is going to report the mean that it has estimated. In fact, it is going to report alpha, and then it is going to tell you how many observations were used in the time series. That may be a bit of a surprise to us. I am supplying, let us say in this case I have 500 observations, right. That is something that you should know. I have not spoken about it, but you can always look up the data, sorry, and it should tell you. So, there are 500 observations that I am feeding in. You should use those 500 observations. What do you mean by number of observations used in the series? Unfortunately, that is not the case. Remember, your order will tell you how many observations have to be thrown out depending on the method that you are using. And it may seem strange, why do I have to throw out the a few observations? So, if you look at this simple example here, or let us say it is an AR1 that you are going to fit in to the series. When I set up, let us say, the linear regression equation, I am going to set up the regression equation at every observation instant that I have, and then straightforward standard linear least squares solution and so on. So, you will be, when we say setting up the linear regression equation, what you are going to do is you are going to write the predictor form, and require that the predictor or the prediction be driven as close as possible. In this case, it is going to be a least square. If a least squares approach is used, this is what you are going to do, right. So, you have Vk minus V hat of k to the whole square, the sum of that being minimized. This is not the only way, but you should understand the underlying principle. The underlying principle is I have a predictor that I have written using assuming it to be AR1, and D1 is the decision variable, and I want the algorithm to drive D1, to tune D1 such that V hat of k is taken as close as possible to Vk. Now, as close as possible is a qualitative statement. In the least squares approach, what we are saying is drive it in the sense of least Euclidean distance, right. And since we have n observations, we want actually to make sure that all observations, all predictions are as close as possible in the least square, in this Euclidean sense, to their respective observations. And since we cannot afford to just please one observation, we want to actually satisfy all observations, this kind of an approach is taken. That is the idea behind least squares. Now, I have written here the summation running from k equals 0 to n minus 1, assuming of course that our time index always starts from 0, although in R it starts from 1. Now, you should straight away notice that one cannot construct this summation strictly speaking from k equals 0. Why? Yeah, so we do not have to, I have V0, but I do not have V hat of 0, and there is a whole lot of research done on how to handle that. So, about I think about 10 PhDs and a few masters and so on. Okay, how to handle this lack of initial conditions. So, the best thing is, it is a BTech approach, is throw away, forget it. Why? I do not want any PhD, just give me this S grade in this course, I will get my best job in Deutsche Bank and be done. So, k equals 1 to n minus 1, I have thrown away. I said, why unnecessarily create a problem and then try to solve, spend beards and moustaches and so on, grow them and so on. I do not need any of those. I will start my prediction from 1 onwards. Now, I have everything available. Okay, and that is what exactly this AR is routine is asking. How many observations were used? Of course, that depends now on the order. If I were to use a 5th order, I will have to throw away 5 observations. And that is one of the things, drawbacks with this kind of an approach. As you fit higher and higher orders, you will be throwing away that many observations, and that is not good from an estimation viewpoint, particularly when the number of observations is not large. each observation is valuable, it has some information, throwing away is not such a great idea. But when you have large observations, always, you know, when anything is in excess, we become very indulgent and we say, okay, doesn't matter, thoda gaya to gaya, no problem. So, that is the approach we are taking, and the number of observations is exactly that. It says how many observations it used in the series. But again, let me tell you, this is only one of the many approaches that are available. And then it reports, for example, the method itself that is used and the residuals, that is very important, right. When I fit a model, I want to ultimately know whether I have done a good job of modeling, and residuals hold the key. So, this routine not only estimates the parameters for you, but also the residuals. Good.